Welcome back, Mindsetters. I hope you had a nice little break there and you went and did whatever you had to do. You went to the bathroom, you had to go speak to mom, you had to go speak to dad, your brother, your sister, and now everyone has to now stop irritating you, and now you have to pay attention and focus with your pens and pads out and ready to make notes. But on a quick side note, I just want to say happy birthday to Munaka. Hey, thank you for being on the page, and I hope you're enjoying the show. But on that note, this is where I hand over to Phil. Phil, take it away.
Thanks so much, Ty. Okay, well, great that you guys are giving us a little bit of feedback. We're going to start talking about the cells themselves. Okay, so now the question before the break was, well, why would I be carrying one of these around inside my pocket? Well, it would usually be inside something which needs a little bit of energy. Now, first thing that we're going to start talking about is primary cells, not because the word means first, but because primary cells are a very particular type of cell. Now, primary cells, these are cells which can only be used once. Now, most of the time, when you start putting in one of these, the sad thing is, eventually it's going to go flat, it's going to give out all of its energy, and I've got to throw it away. Now, this is one of the things which makes a primary cell a bit of a problem. Primary cells are very useful. I've got the chemicals inside here, and I'm going to show you how the magic happens in a moment, but primary cells can only be used once, and that's one of the major issues of a primary cell, is that primary cells are usable only once. Okay, now they are electrochemical or galvanic cells. Now, please, I want you guys to make sure that you actually know the meaning of these words. Electrochemical or galvanic cells actually do something very, very specific. Electrochemical or galvanic cells, I'm going to use the words interchangeably throughout the show, so you need to know that a galvanic is an electrochemical, and electrochemical is a galvanic. These are the same thing. Okay, so electrochemical or galvanic cells, these do something very specific. They take chemical energy. So what they're doing is they're going to take some chemicals inside them. I buy the chemicals in the shop, and I'm going to take chemical energy, and what I'm going to do with it inside that cell is I'm actually going to take chemical energy and change it, like I said, into electrical energy. Now, that is a one-way process for these guys. Once they've given out all their chemical potential energy, all of it's gone. I actually need to throw away these cells. Now, that's a bit of a pain. That means that I've got to buy an awful lot of these things. So if I'm constantly doing this and I'm constantly switching these out, that is one of the major disadvantages of primary cells. Now we're going to dedicate a little bit of time later on in the show to primary cells and why this particular cell is going to run out and cause problems. Now, I've chosen this particular one. I'm not actually using this one because this one I've already used. It's used up its chemical energy, and there's very little of its cell capacity left. That means that I've used up the chemicals inside here. That's a bit of a problem. I've actually got to take this cell, and now I've got to throw it away. Now, the problem is that you cannot actually throw these guys away safely by throwing them into the dustbin. You should not dispose of primary cells inside the dustbin. What you can do is take them to a recycling center. Now, a whole bunch of you are saying, I can't do that every time there's cells. Now, what I want you to do, and I want to encourage this is your environmentally friendly tip, is to actually take these cells and take them to your local Pick n Pay or your local Woolworths. They've actually got recycling bins directly outside their shops, so they will do the hard work for you. So every time you see one of these and they're flat and you've got to get rid of them, please put them inside a plastic packet and actually take them down to your local shopping center, because they've actually got a place to safely recycle these, and they can actually change them back into new batteries. And that means that the chemicals inside here are not going down deep into the ground. You might say, well, that's not my problem. It is. Now, one of the biggest problems in the world in terms of batteries going to landfills is that some of these have actually got an element called mercury inside. Now, mercury gets inside landfills, it leaches down into the borehole water eventually gets through to the river eventually gets into you, and you don't want that happening. So make sure that you put these batteries in the safe place, and that is not the bin. You should not be throwing these inside the bin. Even when they're finished, please dispose of them properly. Take them to a recycling center, and Pick n Pay and Woolworths have actually got bins outside, so they do all the hard work for you. Okay, so there's your green tip for today. Once I've changed all the chemical potential energy into electrical energy, I'm going to take this and safely dispose of it. Now all these extra little bits and pieces and tips, all these extra pieces of info, you might say, okay, well, do I have to remember that? Well, every time you write a paragraph about these batteries, it's actually useful information to know these extra pieces, because this is a very common place for them to ask Learning Outcomes 3 questions. That is where science applies to the economy, to society, and to the environment. Now, by law, we've got to put some of those learning outcome 3 questions. You guys better know a little bit about the environment, about society and the economy to be able to answer those questions. Learning outcome 3, very often you cannot study. So what we're going to do is give you a couple of tips. Battery recycling is one of those tips. Very often I've actually seen that as one of those things. Okay, so now these primary cells, they can only be used once, and that's one of their major disadvantages. Also, how is that going to affect me economically? That means that I've got to go out and I've got to buy one of these again. So that's one of the major problems with primary cells, is each time I want to use them, I've got to go buy a new one, I've got to buy a fresh one, eventually they're going to go flat. Okay, now when I say that a cell is flat, it's given out all of its chemical energy. And now it's all in the form of electrical energy. I've used it all up. Okay, so now let's take a look at this type of cell. Now, this particular type of cell is very, very useful. It's called the Leclanché cell. Okay, now something else which this is actually called is called the dry cell. Now you might say, okay, well, why wouldn't it be dry? Okay, well, the problem is that you've actually got chemicals inside here which need to react. And the magic of the dry cell is that it actually uses chemicals which are made into an electrolyte. But that electrolyte is in the form of a paste. Okay, now if you start to think about toothpaste, it's around about the same consistency. It's kind of solid, it's not really a liquid, but it's going to stay inside the tube. Now the same thing inside this cell of mine. If I take the cell and I open it up, and you should never do this because there's harmful chemicals inside you can cut yourself. I've actually cut myself before doing this. If you open up a cell, you'll actually find that there is an electrolyte inside there, which is almost the same as toothpaste, except it's this really dark black color. We'll talk about the color in a moment. But let's look at the other pieces of one of these cells. Now, this picture, I've actually asked Ty, and I think, Ty, have you posted it up to the page?
Well, it's actually loading now. So.
Oh, fantastic. Okay, a work in progress. That's great. Okay, so now you're going to see a picture of a cell which is like this, where I've got 2 very different pieces. I've got this tiny little piece up at the top, which has kind of got this extra little knuckle up at the top, all right, and that is my positive electrode. Now that is linked up inside, and you can actually see this picture as if somebody cut this open. I've got a carbon rod attached to that, and that is the positive terminal. So that means that I make a plus sign on the top there. If you go look at a battery, and I actually want you guys to do this with me, is if you go look up at the top, I can actually see a plus symbol right up at the top of this battery. And that's where the carbon rod is attached. Now onto the zinc case down at the bottom, you'll actually find this flat piece down at the bottom. That's where I find my negative terminal. So there it is. And I think it's actually on your diagram. The diagram I've sent through to Ty has actually got these labels in it. But now that top little piece, that little bump, is where there's plus. And the zinc case, the bottom piece, that's where I find my negative. Now you might say, okay, well, plus and minus. How do I actually figure this out? Well, that tiny little bump up at the top, how does all the plus collect there and how does all the minus collect there? Well, we've got different chemical reactions, and this is where your redox is actually going to become very, very useful. Okay, so let's go and take a closer look at some of the chemistry which is happening inside the electrolyte of this. Now, just a reminder of what an electrolyte is. An electrolyte is a conductive substance through which ions move. Okay, so let's actually just write down a note there. So now, an electrolyte over here, it is a conductive, it's usually a liquid. So we can find that it is conductive, and that is usually in the form of ions. So they are conductive, and it's a conductive ionic substance. So that means that there's plus ions and there's minus ions moving around inside there, but an electrolyte is a conductive ionic substance. That's found in between those 2 plates. Now let's try to figure out how we get plus and how we get minus. Well, this is down to some redox. And most of this redox doesn't actually happen on your redox table. So what I'm going to do is I'm going to show you how they're going to give this to you in your final exams, and I'm going to show you exactly what they expect you to do with it. Well, there they are. There's a huge amount of information. Sad to say that it's really, really tiny, but this is how it's going to look in your final, and it looks so confusing. Okay, I start to notice a whole bunch of information. Oh goodness, I've got zinc and I've got MnO2. I'm actually going to ask my producer to put it up on screen if he hasn't. I've got zinc in my first reaction over there, and it's producing a E0 potential of negative 1,04 volts. And the other one is producing a positive potential. Well, this is starting to give me a little bit of a sign as to what's going on here. Now, inside your exam, they will give you exactly something like that. Now, what they expect you to do is to label and then combine these half reactions, which is what we're going to do today. So let's label them first. Zinc is going to zinc 2 plus 2 electrons. The electrons are on the right-hand side. That should tell me something. That means that I've actually got a process called oxidation happening. There is a loss of electrons. So this is oxidation. I know that oxidation is happening to the zinc. And this is one of the reasons that a battery actually stops working after a while. The zinc can no longer oxidize because it's actually formed a layer of oxide on the inside. So oxidation starts to occur. So what we're finding is that there's a loss of electrons, is oxidation, and also, if you remember from electrochemical cells, oxidation always occurs at the anode. Okay, so that's quite important. So oxidation, which occurs at the anode. Well, I'm pretty sure that you've guessed that the other reaction, even though it's so complicated, it's all about the electrons. And in the second equation, I'm actually going to highlight both the electrons. The electrons were on the right when there's oxidation. When there's reduction, the electrons are on the left-hand side, and that makes that into reduction. So there we go. We know that reduction is occurring, and if you know your electrochemical cells, reduction always occurs at the cathode. It's absolutely vital that you know that. Okay, now the thing which is common to both of these is that the first reaction is making electrons. So now electrons, I've got to start to tie this together inside my mind. That means that I'm producing a whole bunch of electrons on the one side of my cell. Well, if you've got a whole bunch of extra electrons, what you've got is a negative charge. Electrons are negative. So if I'm manufacturing electrons like I am in my first reaction, I'm going to find that a whole bunch of electrons are actually going to wait there to escape and go through a circuit and come back around to the other side. Now, my other reaction, which actually happens at the carbon electrode, uses up electrons. I can see that electrons are going in. So what we're going to find is that at that other electron where electrons are being used up, I'm going to find positive. There's too few electrons. So I make electrons here, they go through the circuit, and they come around to my other side. So electrons go out of the negative, around through the circuit, and into the positive. Now that is electron current. It is not the same as conventional current. In grade 10 you learned that conventional current goes from plus to minus. But what actually happens in most cases is that electrons go from negative around to plus. So I know that there's going to be some questions about that. Okay. Now down to the redox part, which I'm really excited about. We're actually going to add these two reactions together. I want you to do this with me. Now, if you've written down the half reaction, the zinc goes to zinc 2 plus 2 electrons, and we've got an E0 cell voltage. That is my first reaction. That made 2 electrons. Now my reduction reaction, lucky for us, also used 2 electrons. So all I need to do to balance this out is to cancel out my electrons. There we go, I'm cancelling them out. Now if I write everything on the left-hand side together and everything on the right-hand side together, what I get is a balanced or net ionic reaction. Now it's so long. All I've done is I've combined everything on the left-hand side together. So what I'm actually going to do is I'm going to highlight them in the same colors. So now everything on the left-hand side, so it's going to be in green. Okay, so there we go. A whole bunch of green. And I've got green all over there. So I've added all of those together. That's how I do this. Now everything on the right-hand side of the arrow, I'm going to highlight in yellow. So let's just make sure that that all goes together. So I've just got zinc 2 plus. The electrons are going to disappear, remember? All right, and there it is. It's a huge, huge, huge amount. But now what I'm sure that you've noticed is that nowhere inside here have I actually got room for carbon to react. Remember that one of the pieces of a Leclanché dry cell is actually that carbon rod which is attached to the top. Carbon is not reactive. Carbon is inert. That means that it's not actually participating anywhere inside these reactions. So now I've got my balanced reaction. And, well, now what I've got to do with this is I've actually got to do a little bit more of a step. There's something else which I want to show you. Something which they can ask you to do is to use the electrode potentials of each one. Now, how on earth do I actually manage to do that? Well, the answer is actually quite simple. I've got to use my redox knowledge and know how to combine these two half reaction voltages. I know that at the zinc, I've got negative 1,04 volts, And on the other side, at the carbon electrode, I've got positive 0.5. How do I actually stick these two together? Well, let's actually do an E0 cell calculation together. So this is how much I can actually expect the battery to produce, or the cell rather. So E0 cell, remember, is E0 cathode. Now that's actually a theta, but just for shorts, very often it's called E0. Okay, so E0 cathode minus E0 anode. Well, lucky for us, we actually spotted which ones those were. So what I'm going to do is my cathode, remember, was positive 0.5, there we go, volts, minus, now this is why I use brackets, minus a negative voltage of 1.04 volts. And what comes out here is positive 1.54 volts. That voltage sounds kind of familiar for a very good reason. That's the voltage of one of these cells. This is a 1.5 volt dry cell. If I go take a look on any one of these cells, you'll actually see that it's 1.5 volts. The reason for that is because I used the paste inside here. It is of the cell type. Now, it doesn't matter how big I make the cell, it's still going to be the same EMF. It's still going to have the same voltage. Now, there's two factors which do change this EMF. Now, those are the concentration and the temperature of the cell. So now I can find that temperature is one of the factors of those. So temperature is one of the factors which affects EMF. Now, one of the little tricks, if you're using one of these cells, is if you want to get the last little piece of energy out of them, is you can actually heat them up in the sun for a very short amount of time. The warmer they are, the more EMF they're going to give out. So they might give you a few more minutes of power. If you're stuck in a tight spot and you don't have any more of these replacement cells, the way to get a little bit more EMF is actually to pump up that temperature, and you get a little bit more power out of these. So temperature is one of the factors. The other factor, and this is the most important one, is the concentration. Now, the concentration of the electrolyte. The concentration as the electrolyte runs out is actually the reason that this is no longer giving out 1.5 volts. If you're watching carefully earlier on in this program, this one only measured 1.4 volts. That means that this cell is about to die. It no longer has any energy left. So I've only got 1.4 instead of 1.5. That means that this cell is relatively flat. You'll notice that any one of these cells, if you measure anything less than around about 1.45 volts, that this cell is on its way out. It no longer has the required energy that I need. Okay, well, I'm busy talking like a motor mouth here. I'm hoping that people are listening.
No, they're following along.
Okay, do you think I should carry on? I think I should. What do you think? Can they handle it?
I think maybe we might want to take a break, because I'm sure you're going to introduce another subject into this.
Absolutely. Oh, okay. Before we do that, let's just recap. There's a whole bunch
Okay.
of info. Okay, so just to revise what we were talking about. Okay, well, this is a huge amount of information on one board. So what I'm going to do is I'm going to talk you way through this. Okay. First of all, we identified my oxidation reaction. The way that we did that was by spotting that electrons were coming out on the right-hand side. That was happening at the zinc electrode. So that's all the way at the bottom here. On the other side, we saw that there was actually something happening. Our electrolyte, manganese dioxide, that's the black stuff inside here. It's a very dark black color. Plus ammonium chloride. And now I'm pretty sure that you guys have noticed sometimes when these batteries get kind of damaged or inside a device which has got these, you'll find a white substance. Now, a lot of people seem to think that that is an acid. Now, it's not so much an acid as a salt, and that is ammonium chloride. That's actually a salt which is leaking out of the electrolyte here. It's not toxic. It's not going to poison you. In fact, ammonium chloride has actually been used in cough syrup. So please don't be afraid of it. That little white fluffy stuff is not going to harm you. Just wash it off with a wet cloth. Okay, so manganese dioxide and ammonium chloride, those form the paste inside here. What happens to them is they actually get reduced and eventually run out. Now, one of the things that actually starts to happen inside here is that paste can dry out, and that's one of the reasons really old batteries no longer work. So, once I've done my oxidation of zinc and my reduction of manganese dioxide, I've now got a combined electrochemical cell. Just a reminder that they can do this to you. You need to identify which one is oxidation reduction, and that gets you which one is the anode and the cathode. Why would I want to do that? Well, that allows me to figure out how much voltage I can expect from one of these cells. And that's very, very important. If I know the anode, if I know the cathode, I can do an E naught cell is equal to cathode minus anode. And that gets me a voltage. And I actually managed to predict, without looking on the side of the cell, that this one can give me an EMF, an electromotive force, of 1.54 volts. And that is it. Just remember your two factors which can affect the performance of this battery. One is temperature, because the hotter it is, the more EMF it gives, and the concentration. As the concentration of electrolyte goes up, the more EMF. But now the problem is when it starts running out or getting too cold, the EMF drops in both cases. I think it's time for that break. What do you think, Ty?
Definitely. But also wanted to make a note out there because I've been hearing a lot of people saying, oh, I want to go explore with our batteries. I was like, but guys, you have to be still very, very careful.
Absolutely.
Preferably do it at school with the teacher supervising because this stuff can get dangerous. And yeah, some of the liquids in there are toxic.
Absolutely.
Exactly. So mindset is be careful. But on that note, make sure you come back and we'll see you after this break.